and we're going to produce a sequence of token of the corresponding lexeme as output. And once we have this tokens, then we have to give it to the next phase. So the next phase is what we call it as uh, parsing, or what we call it as syntax analysis. Okay. So let's just see this is structure. So this is how lexical analyzer and the next phase, that is syntax analyzer, works out. So whenever you find the term like parser, it means the next phase, that is syntax analyzer. Okay. So you may find the term parser uh, anytime. So it is nothing but the next phase, that is what we call it as syntax analysis or syntax analyzer. So you'll have your lexical analyzer, then you'll have your syntax analyzer or parser. So whatever the source program you give, you'll get the output as token, and it will be given to the next phase, that is parser or the syntax analyzer. And we use a call, that is get next token, to ask for a new token once one token is finished. Okay. So this is the interaction between your lexical analyzer and the next phase, that is syntax analyzer or parser. And so lexical analyzer also have an other role, like it will just strip out your comments, white space, and it will have the task of correlating error message generated by the compiler with the source program. So we have even discussed this in the previous videos also, that your removal of your comments, white space, or any. So removal of your comment, white space are done by the lexical analyzer. Okay. So a lexical analyzer can be seen as the process of uh, in the way of two process. So the first as scanning, and the second as lexical analysis. So when we say, we also refer this lexical analyzer as scanning. So when we say scanning, we are just scanning the whole or the line of code. And when we talk about lexical analysis, we speak about more about the converting the scan input to the tokens. So the next question is, why we have this lexical analysis and why we have syntax analysis, or why we have this parsing. Okay. So we know that lexical analysis converts the stream of character into tokens and then give it to the parser. So the question is, can we combine just two phases into one? So the answer is simple, that to make it more simple, we divide this into different phases, that is lexical analysis and syntax analysis. They work coordinately, and the reason for being separate phases is over here. So the first reason is, when we separate this into different phases, there is simplicity of the design, then there is compiler efficiency is also improved, then the compiler portability. Just a second. So separating your lexical analysis and the syntax analysis has few reasons. The number one is your simplicity of the design. Next is compiler efficiency is improved. Then this compiler portability is also enhanced. So considering these few reasons, they have make this lexical analysis and syntax analysis phase separately. Okay, so here also even look. So as I mentioned before, you may find syntax analysis or parsing. So when we say parsing or parser, it refers to the second phase, that is syntax analysis. When we say lexical analysis or scanning, it refers to the first phase of the compiler. Okay. Then tokens, pattern, lexeme, I think we have discussed it in the videos also. Even you may have seen finding the number of tokens for a given line of code. Okay, I'll just skip this one. Then when we are talking about lexical error, just a second. So when we are talking about lexical error, it is difficult to give the lexical error without other components. So it works closely with the parser to even generate or give this lexical analyzer, lexical error. Okay. So in short, your lexical analyzer and the next phase, that is syntax analyzer, works closely together, even with regard to the error generation also. So for example, so if we find this line of code fi, so when the lexical analyzer find when we lexical analyzer find this fi, so it get confused whether this is an identifier or is this a misspelling of if statement. Okay, so when the lexical analyzer just look at this statement, it is difficult to conclude whether this is an identifier or this is a misspelling of if statement. Okay, so it when it work with parser and it have the idea of whether there's any declaration of any identifier with fi. So if there is any declaration as in or care or whatever it may be, so it will then understand that this fi is not a misspelling of if. And if there is no declaration of fi in the previous line of code, then we know that it is a misspelling, or if this is going to generate some error. Okay, so this is about error. And for error recovery in this lexical analysis phase, we may have this panic mode recovery, where we delete successive character from the remaining input until we find a token of that uh, token of corresponding lexeme or pattern. Okay, so we have other error recovery action also, like we delete one character from the remaining input, or we insert a missing character into the remaining input, or we have replace a character by another character, or transpose two adjacent characters. So in this error recovery actions, all we're trying to do is whenever we find something that doesn't correspond to a token, we try to match it with a corresponding token. So we may take this few action as listed over here and match it to a corresponding token. Okay. there are few other topics. This topic you must have studied in flat finite automata and other things. So yeah, I'm just highlighting few of them. So even regular expression, even I have sent you in the notes also. So few things I'll just highlight over here. So as we know that whenever you find letter, you can say that letter with underscore here. This is our definition, right? It's going letter means it's going to contain capital letter A to Z, then small letter A to Z, then underscore. For this particular case, here we include an underscore. So when we ever we think about digit, it's going to be from 0 to 9. So whenever we have identifier, it's going to be here. So meaning that this is our regular definitions that we may use in the later classes. So here also few of them are there digit then other things so related to the problem given. So this thing you must have seen thoroughly in played also. Once you have the idea of regular expression and regular definition, then then it is easier to work out with this lexical analysis. Okay. Then so, so everyone note down this statement. This you can just screenshot it or you can just write down it. You're going to use this statement like many times in the remaining chapters. Okay, so this is a grammar for branching statement. We have the first as statement which is nothing but of if expression then statement then or if statement then statement else statement then epsilon empty. Then another one is so this the first one is the definition of your statement, the second is definition of we use expression, so definition of expression then definition of term. So for expression term then relational operation then term then or expression may contain term only. So and what is included in term is identifier or number. Okay, so you may use this statement multiple of times and it will be written in the short form. So here it is written in the long form. So in while working out, you may find IETS, IETSES like that. Okay, here it will be TR, TT. So then ID will be ID, then number may be by N. So like this statement is going to be used many times. So just note it down. Okay. So once, so these are all our definitions or pattern of a token. So even this is also you can just look through it. And white space also these are definitions. So I'll send this PPT as well. You can just go through it. Then another one is just note down this one also. So here you have all those lexeme and the corresponding token name and corresponding attributes value. Okay, for any white space there is no token name. Whenever we find any white space we are going to just ignore it. So if you have if then it corresponds to the token name. If then means then, else means else, and if you find any identifier then we are going to use identifier, and if we find any number then we are going to use the number, and the attribute value is given over here. So if you have an identifier, we're going to make the entry in the table, symbol table, and the pointer is going to point to that particular entry. For number also same. Then we may have this other relational operator like less than. So we may use LT, less than, then less than or equal to, then equal to, then not equal to, then greater than or equal to. Okay. So just not just screenshot this page as well. This figure 3.12. So it may be used solely. Okay. So all these few topics that are included in this chapter are all from plane. Like you have this regular expression, then regular definition, then transition diagrams. These are all you have studied in plane thoroughly. Okay, then so as I mentioned before, transition diagrams. So with as you know that transition diagrams gives you the direction of whether it corresponds to a particular token or not. So let's see an example over here. This is the transition diagram for the relational operators. Okay. So as you know that whenever we have transition diagrams, you will have this circle type, then you have this double circle to tell that it corresponds to some particular token or it's the end of some thing that matches to some token. Okay. So 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 whenever if we go the first one, that is you'll have less than, then it will, if you go to the second, that is number 2, then it is less than or equal to, so it corresponds to less than or equal to. And if we look for 3, it is less than and greater than, it corresponds to the symbol of not equal to. So and if we have less than, and if we have any other than this thing, it just corresponds to that, it is just less than, so it will return the relational operator as less than. Okay. So this is how your transition diagrams works to help in identifying the particular tokens, because so it gives a confusion. So when we don't have all the so if the compiler only read the less than, and if it doesn't, if it conclude that it's just less than, then it becomes a not accurate if we find equal to in the next character. Okay. So this transition diagrams also helps in identifying the tokens correctly. So for this identification of these tokens correctly, we may use other tools also. So for identification of tokens, as I mentioned before, we may use like tools like to read. Only reading one character at a time doesn't give the confirmation of a token, as I have just mentioned before. Like if you have just read less than, and if there is any character right equal to, then if we confirm that it is just less than, then it gives you the wrong output. So for working out with this type of thing, we have some tools like buffers and sentinels that will read more than one character at a time. Okay, so you'll find all those in this node also. So so the important part that I was trying to focus for today is this lexical analyzer generator. So whatever uh, we are going to start the program in the lab once we are done with this topic. Okay. So what is this lexical analyzer generator Lex? So it is nothing but a tool. We also call it Lex, or other name is Flex. So it's going to help in generating the token. Okay. So your Lex allow so it allow one to specify a lexical analyzer by specifying regular expression to describe patterns for tokens. The input notation for the Lex tool is referred to as a Lex language, and the tool itself is the Lex compiler. Okay, so we're going to write the program, and the language that we use is what we call it as Lex, and the tool itself, or this lexical analyzer generator, is nothing but Lex compiler. And so it's going to generate a file. Okay, so it's going to generate a final file that contain all the patterns, like, so if it has to be if, then it has to include the pattern of if, then means then, and for identifier it has to include the pattern means those definitions. Okay, those, so if definitions of identifier, so if an identifier matches with that pattern, then we can conclude that uh, it gives a identifier as token. So here Lex will do that work. So before reading this thing, let me show the diagram first, then you'll understand it. So how lexical analyzer is going to create it. So first you'll have this Lex source program with the extension .l. Okay, so, and the language is, as I mentioned before, Lex. So you're going to write the program with the extension .l. So Lex.l. So then it has to be compiled with this Lex tool, that is Lex compiler, and it will generate a file as output, that is lex.yy.c. Okay, so it will generate this lex.yy.c. So once we have this lex.yyc, we are going to give it to the C compiler. Okay, this C compiler will give you the output file as a.out. Right, every time your C compiler compiles, it gives the output in the file a.out. So a.out is nothing but it contains all the patterns that about the tokens you wrote in this Lex file. Okay, so all those token of if else identifiers, or all those relational operators, so all different patterns that we write is finally containing in this output, that is a.out. So this a.out contain all those patterns. So once we have this a.out, so then only we are going to generate the tokens. So here we are going to give the input stream, and it has to go through this a.out, where it contains all different patterns. So according to which pattern it matches, it's going to return the tokens of those character stream or input stream. Okay, so this is how lexical analyzer is created. So you can look here. So your Lex compiler transform the input patterns into a transition diagram and generate code in a file called lex.yy.c that simulates this transition diagram. So once you have this lex.yyc, then we are going to give, as mentioned before, that in the C compiler to obtain a .out. So here is also more definition that we have used the file lex.l written in the Lex language, and here we are going to describe the lexical analyzer to be generated. When we say lexical analyzer to be generated, it refers the patterns or the definitions. So what are the patterns that we want to include in that? So your C compiler is going to transform this lex.l to a C program, as mentioned before, that lex.yy.c. Okay, and this is going to be compiled by C compiler. Okay, so it so there are other few things that are included over here. Okay. So like so your a dot out is nothing but a C function that returns an integer, which is a code for one of the possible token names. Okay, just a second. Okay, just a second. So our aim is to include all the patterns or whatever the tokens that we want to generate. We have to include it in this a.out patterns, in this a.out files, and it will just check with the input stream line which pattern it corresponds to, and it will return the token as the output. Okay, now let's see how we can write this lex program. So your lex program consists of this structure. The structure is over here. It's going to contain three sections. So the first one is declarations, then you'll have translation rules, then you have auxiliary functions. So it's going to contain three sections. So remember that a Lex program is going to contain three sections: declarations, translation rules, auxiliary functions. So the first section is declaration. So what we are going to include in declaration is declaration of variable, manifest constraint, identifier declared to stand for a constraint, example, name of a token, and regular definitions. Okay, so declaration is going to contain all this information. So once we have declaration section, then next is translation rules. So in this, mainly in this translation rules, we are going to include all those patterns and what has to be done when we find that pattern. Okay. So this second rule section, that is translation rule, here it will have the form that is pattern then action. So here we are going to write our definition, and here we are going to write our action. So each pattern is nothing but a regular expression which may use the regular definition of the declaration section. And the action is nothing but a fragment of code typically written in C, although many variant of Lex using other languages have been created. So in short, we're going to write our regular expression or the patterns over here and what has to be done when that pattern is missed. Then when we then you have this auxiliary function. So here we are going to we're going to have some additional functions, right? So we're going to have some additional function. So these are going to be placed in this auxiliary functions. Okay. So let's see this structure. This is So do you see this screen properly, clearly, everyone? Am I audible to you?
Yes, sir.
Okay, okay. Then I assume that you see it clearly. So look here. So so this first so this part is our, that is first section, that is declaration part. So okay, so here we have all those definition of manifest content, then regular definitions. So all has been included in this declaration part. Okay, so this given is a lex program for that particular figure 3.12 that I told you to just note it down when I to the class. So this one that I highlighted is the first section. Okay, each section will be separated by this double percentage symbol. Okay, so this is our first declaration section. Then this is our next section, that is so this is our next section, that is transition rules, and the remaining this section is our auxiliary function. Okay, so so this is our transition. This first part is our declaration section, and this part is our translation section, and this third part is our auxiliary function. Okay, so if we look over here, so we have all those definitions. So if you have okay, so here we just include all those definition of delimiter, then white space, letter, digit, identifier, then number. Then here once we have this definition, here we are going to do the pattern with action. Okay, this in this translation rules we're going to have pattern. So whenever we find white space, what we are going to do, we're not going to do any action, so we leave it as empty. If we find the pattern if, then we are going to just return the token as if. If we find the token, then return as then. If we find the as else, then we are going to return as else. And if we find identifier, pattern of identifier, then we are going to return as identifier. And if we are going to return find any number, then we are going to return number again. And if you find less than, then we are going to return as relational operator. Okay, similarly for other case also relational operator. Then we include other auxiliary functions that are needed for the program. Okay, so we'll wind up with this, and in the next class we'll again discuss about this lexical analysis generator, and we'll write a new program on that. Okay, for today just I'll just send you this note, you can just go through it, then we'll discuss it again in the next class. Okay, and everyone just leave your attendance in the comment box, and you can leave.